Okay, welcome. So I am Scott Baker. This presentation is going to be on XOS. XOS is the service composition and management layer that's used in Cord and SEBA, and I work for ONF. So the problem we're tasked for here is managing services in Cord. So there's a large set of services, so managing them is a fairly large space. It decomposes into a couple of different problems. The first problem is what I called container lifecycle management. So we have services, they have compute resources, those services need to run in containers, you need to deploy them on hardware, you need to schedule them, so you may have 10 containers and 5 nodes, you've got to figure out how to partition those 10 containers amongst those 5 nodes. And then you've got to deal with failures. So if a node goes down, you have to migrate your services off that node onto another node. That first part of the problem was container lifecycle management. The second part of the problem we called service coordination. And that's sort of a more higher level problem and has to do with how to make your services work together. So sometimes you have services that they were not designed together. They might be third-party services. They might be other open source services. But you've still got to have abstractions that will span across those multiple services. So for the first part of the problem, the container lifecycle management, we already have a robust set of open source tools that is able to deal with that. So you've got Docker. Docker will give you isolation between containers so that your processes in one container cannot interfere with your processes in another. Kubernetes will take the scheduling task. So you can give Kubernetes a list of nodes and a list of containers, and it will schedule those nodes to those, or will schedule those containers to those nodes. Helm bills itself as the Kubernetes package manager. Helm will manage dependencies, so you can build up a chart that has many subcomponents, and it will ensure that all of the subcomponents are installed necessary to make your chart work. So those 3 tools pretty much handle the container lifecycle management part of the problem for us. And we're not going to try to replace those. We're going to move on with the second half of the problem, which is coordinating multiple services to work together. And that's what XOS does. It manages these different services. So this breaks down into 3 parts. The first part is unification. And unification is to take all of these different services and to provide sort of a similar user interface and API to them. We do that to avoid the n times n problem where you might have n northbound consumers of the system and m providers of services, and you don't want to have every pairwise combination where every consumer has to know the specific API of every provider. The other 2 problems we have are coordination and synchronization. So synchronization is kind of a horizontal problem in that you have many services working together to provide a chain of connectivity for the subscriber so he can get out to the internet. And these services might have to talk to one another in order to do that job. And you also might have to have some state that spans these services and will need a place to store that state. Synchronization is a north-south problem. So you'll have directives coming into the top from, like, the operator wants to, for example, authorize an ONU. You'll also have status coming up from the bottom, so an ONU has authenticated itself or an ONU's connectivity has been lost. You kind of do a rendezvous in the middle there, and you always want to kind of converge on the desired state that the operator wanted. So one question people always ask is, why did we invent our own thing with XOS? Why didn't we just choose some other solution to the problem? And the reason we went with our own is we wanted to integrate lots of different kinds of technologies. So this is kind of a multi-cloud type approach here, where you might have both Kubernetes and OpenStack. And you might have services that span those, services deployed on each of those that will need to cooperate. So neither one of those APIs, neither one of those products is sufficient in and of itself. Even just having 2 different Kubernetes, you might have a local Kubernetes versus a Google Cloud Kubernetes, where the security implications might be different. Your networking, maybe you could use Kubernetes or OpenStack's networking, but maybe you want to use ONOS's. We've also got events with Kafka down there in the end, and log storage and monitoring with Kibana. So XOS, by rolling our own, we could kind of have an umbrella that could encompass many different technologies. So unification, as I mentioned before, is to avoid that n times n scenario. So we've got all these different operators across the top that all want to use Cord. We've got all these different services that people have written across the bottom. We don't want every operator to have to know the API for every service. So we put Cord in the middle. And we also wanted Cord to be an extensible platform. So as you add new services, the platform is able to extend to accommodate those new services. Now, we like to think of XOS as operationalizing Cord. So over here we have a typical pod. You have hardware down at the bottom, so your switches and your compute. You have some services managing those hardware, so ONOS and Kubernetes. VNFs and control applications implemented in ONOS and Kubernetes. Then you have the Cord controller, which involves XOS at the top. Lately in SEBA, we've been calling that top part the NEM, the Network Edge Mediator. So looks like the font got a little bit messed up over there, but recipes will come in via Tosca up at the top, and those will feed into the northbound API of XOS and is used to configure and provision the rest of the system. So Tosca recipes are something we can do at deployment time, or we can do them dynamically at runtime as the system changes. You also have Protobuf, XPROTO models. Those go into XOS to configure modeling. You would typically also set your modeling up at deployment time, but it is also something that has a dynamic aspect as you add new services. Helm Charts, because we're letting Helm and Kubernetes do that container lifecycle management, you can supply Helm Charts directly to Kubernetes, and Kubernetes will go ahead and schedule your containers out on your nodes. And then, of course, we've got Kubernetes at the bottom managing the compute hardware. Now, this whole thing is a dynamic system, so things will change over time. You know, the Kubernetes state will change, pods will go up and down. You know, you might deploy new Helm Charts, you might add new modeling, and you might send in new Tosca recipes to provision new services. So we think of that part over there as kind of, I would call it service lifecycle management as opposed to container lifecycle management, because it's more than just managing the containers. It's also about managing the modeling and the, those abstractions that span multiple services. So all of this is part of our first task, which is unification. And unification, the unifying abstraction we have is the XOS Data Model. Now, the XOS Data Model, it's got both base models, which is stuff you get for free, and it's got models that you can extend later yourself. So the base model is, you know, your users and your permissions, compute and network resources, so things like Kubernetes, pods, OpenStack VMs, networks, routes, stuff like that. We have a whole service tenancy and dependency model, which is how you construct dependency graphs of services and how you construct data plane chains for subscribers. Yeah, and then that all comes as part of the data model that is just delivered to you. You get that automatically. By implementing your own service, you can extend the data model. So you can create your own models in there for data items that might be private to you. Plus, you can also inherit from the base models and extend the functionality of the base. So this is very object-oriented type approach where you can inherit from those bases, contribute new functionality, and then other people who want to use the base functionality of your augmented model can do so without having to necessarily know about the augmentations that you've added to it. I'm going to work through a little bit of a running example in this presentation, which is the Volt service. The Volt service, or virtual OLT, is what manages OLT devices, ONUs, and such in a SEBA pod. So the Volt service is what's carved out in kind of this dashed line. And it's in between two other services in the service graph. So to the west of it is the RCord service, which manages individual residential subscribers. And to the east of it, over there, is the Fabric Cross Connect service, which manages flows through the aggregation switch. In between is the Volt service, which handles OLT devices and such. So there's kind of this gold set of models and this blue set of models. The gold ones are the service models, and those have global parameters for the entire service. So there's typically one VOLT service, so that would hold any global state for that VOLT service. And the blue ones represent the per subscriber tenant aspect of that service. So for example, if I am a residential subscriber, then I need a point of presence somewhere in the RCord service, in the Volt service, and in the Fabric Cross Connect in order to get my packets from my house out to the internet. And that's what those blue boxes represent, is the little piece of the Volt service that belongs to me. And then these green ones are other models that the Volt service has added to implement its custom functionality. So the Volt service, it needs to know about OLT devices, and OLT devices, they'll have NNI ports and PON ports. It needs to know about ONU devices, which will be connected to an OLT via a PON port. And it needs to know about UNIs, which are connected via the ONU device. So we, in order to provide that unification, we use something we called XPROTO. And XPROTO is based on Google Protobuf. It's almost straight Protobuf, but we added a little bit of syntactic sugar to it to give it some more features. And the main contribution we've added is relational features, so that various messages in XPROTO can relate to other messages. And you've noticed that on the previous graph, we had lots of little lines between the various boxes. Those are relations which occur in the data model. So XPROTO is our augmentation of Protobuf to allow that. And the key thing with XPROTO is we have a tool called XOS Gen X, which will auto-generate various other artifacts in the system. And the key idea there is that a developer, rather than having every time he makes a change to go change 6 different things, for example, you've added a new field to a model, now you need to add something to the command line interface, you need to add something to the GUI, you need to add a new gRPC stub, etc. Instead of doing all that, you just add it to the XPROTO. You run it through XOS Gen X, and it will auto-generate all of those features for you. This is an example of some XPROTO. I'm not going to go into any detail on this. This is kind of expected to be an overview talk, not a detailed walk through the code. But just to understand, this is the XPROTO for an ONU device. If you're familiar with Protobuf, you'll see a lot of Protobuf in this. For example, it's called a message. We've added a little bit of our extensions. Like you can see, there's an XOS base at the very top that indicates inheritance. The many to one, about the 4th line down, that is a relation. There's some stuff over here on the side, some help text, and some choices fields which might be useful in the GUI or the command line interface. There's some things about feedback state, which are used to augment the direction of data flow through the data model. All of that, the richness of what we've added with XPROTO, allows us to generate all of those different artifacts. So that was our first goal, was unification. Our second goal is coordination. And unification, it sort of automatically facilitates coordination, because by having this unified data model, it's easy for services to talk to one another by using the data model to extract state about each other. Coordination is fundamentally an east-west process. Here we have a chart. It does show some top-down directives and some bottom-up activity. So top-down, again, is things like the operator, where bottom-up is stuff like ONU statuses and connectivity statuses. But coordination is mostly this middle line in there, which is intercomponent state. And you might imagine you have several different services, 5 of them there that are implementing the connectivity for a residential subscriber. Each one might need to specify some state to its neighbor so that the neighbor knows how to configure itself. So imagine one of them is the OLT service. Someone might need to know what tags are set on the OLT service. And that is the coordination aspect. An example here, concrete example using a couple of the SEBA services. We have the RCord subscriber service. It knows about subscribers, so it knows about C tags, S tags, ONU serial numbers, IPs, and MAC addresses. The OLT service knows about OLT devices, ONU devices, so it knows, for example, that the OLT devices are attached to a particular port on the aggregation switch. And then we had that third service over to the side, which was the Fabric Cross Connect. And it was responsible for programming flows from the OLT out to the internet, so out to the BNG, for example. And it needed to know, in order to program those, it needed to know an S tag, and it needed to know which aggregation switch, and the source port on the switch, and the destination port on the switch. And so because we have this unified data model, the Fabric Cross Connect service can just pull that information from the appropriate places. So the S tag it can get out of the subscriber object, the switch ID and the switch port it can get out of the OLT device, and then the destination port was actually some state that was programmed into the Fabric Cross Connect service itself. So coordination, where does you actually implement this in XOS? This is typically implemented in something we call a model policy. And model policies are triggered when various events happen. So if an object is created, updated, or deleted, it will typically cause a model policy to be fired if there is a model policy for that particular data model object. Not all objects have model policies. You really only implement them when you need that type of functionality. And the thing about a model policy, it always causes changes to be pushed back to the data model. It never causes changes to go out to an external component. So there'll never be a policy that, for example, makes a REST API call to Volta or ONOS. The control flow always goes back into the data model. And where we implement these policies is in service-specific synchronizers. So this is getting a little bit into the container architecture that we use with XOS. So there is something called the XOS Core up at the top. The XOS Core implements our API, our database storage, things like that. And there are these synchronizer containers. Each synchronizer container is provided by a service. So if you have written the foo service, then you have likely provided a foo synchronizer container. So it's very simple. Your policy is watching for a change on model foo, and whenever it sees a change on model foo, it applies a change on model bar. That's just a sort of a very simple example of a model policy. I'll go through an actual working example from the VOLT service. Recall that's the service that manages OLTs and ONUs, and it's sort of sandwiched in between the RCord subscriber service and the Fabric Cross Connect service. The subscriber service having all that subscriber state, the Fabric Cross Connect service being responsible for programming the AG switch. So typically the way a chain is constructed in XOS for a subscriber, it's a step-by-step process where each element in the chain is responsible for constructing its eastbound neighbor. So let's say a new subscriber was created. So someone created an RCord subscriber object. That RCord subscriber object would have then created a Volt service instance, because that service instance will hold that subscriber's point of presence in the XOS data model. So as soon as that Volt service instance was created, that will cause the Volt service instance model policy to run. And its first job is to create the next thing in its chain. So the Vault service instance knows that in order to get its packets from its OLT out to the internet, it's going to need a point of presence in the Fabric Cross Connect service. So it creates a Fabric Cross Connect service instance object in the data model, and it links it back to itself. Now, it also knows that it needs to associate an ONU device because each residential subscriber does have an ONU associated with them. So it will go back here and it will look in the subscriber object and see what serial number has the operator said that subscriber should have for his ONU. I'll retrieve that serial number. Then I will search for an ONU device in my inventory. And then when I find that ONU device with that serial number, I will link it. Now we've completely set up the Vault service instance. We have everything necessary to plumb that particular residential subscriber through to the internet. So that was coordination. The next task is synchronization. And synchronization, if coordination was something that always went back to the data model, synchronization is something that always goes outside of the data model. Synchronization also occurs in the Synchroniser container. So the Synchroniser container is kind of where we put all of a service's code that interacts with XOS. It has the policies, it has sync steps. So we're going to now talk about the sync steps, which are what handle the coordination between XOS and external services. So synchronization is a north-south process. So again, we have top-down directives. Those are things like the operator whitelisting an ONU or the operator adding or deleting an OLT. And then we have the bottom-up activity, which could be things like success or fail. You know, like maybe an ONU is in a failed state. Maybe we've lost connectivity to a subscriber or to a subscriber's ONU. So we've always have to worry about trying to enforce what the top-down directive has said, that's the desired state, making the actual state comply with that. So we have this rendezvous in the middle where we will try to bring that into compliance. Now, as a concrete example of this, we have the ATT Workflow. I don't know if there'll be a more in-depth presentation on the ATT Workflow in the conference here. I would think there probably will. But I have very much summarized and cut out some big chunks of it in order to make it fit all on one slide here. So this is just a typical what might be involved in synchronization. So in this case, let's say the operator wants to use the API to XOS in order to whitelist an ONU. Whitelisting an ONU involves the serial number and the PON port ID. That's the parameters the operator would supply. So what he'll do is he'll first create an ATT Workflow driver whitelist entry. Whoops. That's kind of a long name for a model, but that's just what we called it. Basically, the first half of it identifies the service, and the second half, whitelist entry, is what it does. And that object in the data model has the serial number and the PON port. So the next thing the workflow will do is it'll check to see, you know, does that ONU exist, and is that ONU with that serial number on the correct PON port? If it's not on the right PON port, then there's a problem because the operator has not authorized that ONU to be on that particular PON port. So it'll set its state to disabled, and it'll reset the authentication state. Then it'll make a REST call to Volta to disable that ONU. So that is an actual synchronization action there, that REST call, because we made a call outside of XOS into an external service. So in the case that the ONU was on the right PON port, then we can make a REST call to Volta to enable the ONU. Once we've enabled it, we need to wait for some things to actually happen. It doesn't, you know, get activated and authenticated immediately. We actually have to wait for some events to come in to say the ONU was activated, and then that the ONU was authenticated. And then once those happen, we can set its state to approved, its status to enabled, And then we move on to an entirely different state machine, which implements a DHCP workflow. So to give you an idea of everything that happens with this workflow, this is just a picture I grabbed off of the guide on OpenCord. And this illustrates the whole workflow. I'm not going to really describe any of this. The whole point is just to understand that there are many different steps in here and many different synchronization actions, you know, like this yellow box where someone made a REST call to enable an ONU. Or, you know, over here, someone made a REST call out to enable a subscriber. Those are all things that have to happen during synchronization. So there are 4 kinds of steps that deal with this. The first 2 steps are downward control flow, so control flow from XOS to the underlying service. Those are called the sync step and the delete step. So the sync step is whenever you've created or altered an object in XOS, it'll run that, and it is to take the underlying service and to enact that state on it. It always continues retrying until it succeeds, so if there is a temporary failure, it'll just spin around in a loop and try it later. If it somehow gets out of consistency, then it may retry it later. If it has something has gone wrong and we're doing things in the wrong order of steps and something's not ready yet, it'll always come back and try it again. And as a concrete example of that, let's say an OLT device, someone created it in the XOS Data Model. The sync steps job would be to make a REST call to create that OLT in Volta. The delete step does the exact opposite of a sync step. That's what happens when someone deletes an object in XOS. So we don't wipe it from the data model immediately. We kind of keep it around in this soft deleted state until a delete step runs to actually go into the underlying service and ensure that is deleted, and then we can do a hard delete in XOS and completely forget about it from the data model. So if those were the 2 downward steps, there's also 2 upward steps, and those are the poll step and the event step. So the poll step is just what it sounds like. It's a polling loop. So there's typically a big while loop, and every X number of seconds it will make some calls into the underlying service and query it for some objects. So an example is maybe it is polling Volta to query the set of OLT devices and ONU devices. And when it finds new ones, it adds them to the data model. The event step is just like the poll step, but instead of using a polling mechanism, it uses an event system like Kafka. And typically what we have here is things like ONU authentication events, ONU DHCP state events. When we see those come in, we will update the ONU device with that change in state. And that is, you know, upward flow in the data model. Now, it's important to note that as stuff is updated in the data model, it might actually trigger a model policy, which then might trigger some other sync step. So take, for example, what happens when an ONU is validated when its authentication is succeeded. We get an event that says, you know, the ONU has authenticated, so we update the ONU device and the ATT Workflow driver service instance with that state. But that causes other model policies to fire, which will then cause other actions, which may then in turn result in sync steps activating and making a REST call to something. So where does the sync steps live? Well, they also live in a Synchroniser container. So the Synchroniser container, it contains model policies and sync steps. If you recall the diagram I had a few minutes ago, the key difference is rather than an arrow pointing back up to the XOS core, we have an arrow pointing outward. And here in the case, someone changed an OLT device in the data model, the sync step becomes activated, and we make a REST call to Volta that says update that OLT device. So this is about the end of the talk. So I usually like to end with a request for ways that people could get involved. Some things we can use is integration of existing services, so there's lots of open source services out there. Things like Cassandra, Nagios, various CDNs. If people were to take those services, write a synchronizer, do the modeling, you could make them available in Cord. They would be easy building blocks for other people to use. It's easiest to build a service when you have lots of useful building blocks. The other thing, invent new services. So, like a firewall VNF, a parental control VNF. I think the Telefonica talk had, lots of examples of very useful VNFs that could be implemented and things that could be put on the edge. So implementing some stuff like that, making it available via synchronizers to XOS, and then it becomes something that people can easily add and enable in their Cord and SEBA pods. So that's it.
Thank you, Scott. Does anyone have any questions? Yes?
Thanks for the nice talk. I have one question regarding this synchronization. So if somebody has given some Tosca template, some command from up, so it is a synchronous call or asynchronous call? Because basically, the application who is giving that call has to wait for the response because things below are asynchronous in the sense.
Yeah, so pretty much everything is asynchronous. So when you make a call in through the northbound API that says update some object in the data model, it returns immediately. And then some synchronizer will notice that update and run a policy or run a sync step. And later on, it'll update a status in the data model. It says, OK, I succeeded. So if you are someone on the northbound side who would like sort of synchronous behavior, you want to do something and get the result, it's kind of up to you to do it, put it in the system, wait for it to happen, and pull for it later and say, OK, did it succeed? OK, good. What I wanted to succeed did.